Okay, this is project 6 video, project test 6 video, number 4, problems 31 to 40. An experiment was conducted to investigate the relationship between the dose of pain medication and the number of hours of pain relief. 20 individuals with chronic pain were randomly assigned to one of 5 doses. All right, we have a dose of nothing, a half, 1, 1.5, and 2, and they're marked down here. The results are shown in the scatter plot below. The data were used to fit a least squares regression line to predict the number of hours of pain relief for a given dose. Which of the following would be revealed by a plot of the residuals of the regression versus the dose? First off, if they're fitting a least squares regression line, we should do the same and just see what we have. And if I'm drawing this thing, I'm not sure exactly where it's going, but probably somewhere about here. And there's my least squares regression line. All right, so they're talking about the residuals. Now residuals is the vertical distance from the line. And here I'll go, wow, we're really close to the line. So I got a small residual here, and up here I'm starting to get very, very large residuals. So as I move, or as my dosage increase, as dosage increases, my residuals increase. Dose increase, the residuals increase. And basically the residuals is just what we observed minus from the predicted. The sum of the residuals is less than 0. By the way, that'll never be the case, as sum of the residuals is 0, always. All right? The sum of the residuals is greater than 0. No, the sum of the residuals equals 0, because this one cancels out this one cancels out this cancels this. So basically the sum of the residuals is 0. That's an always, always. There are outliers with lower doses. When I look out over here, I'm like, gosh, it's really close to the regression line. Probably not the case. And a residual plot might not show that. The variation in the hours of pain relief is not the same. All right. As I move farther out, I definitely see greater variation, greater spread. So D, the variation is not the same. All right. And then it talks about there's a positive linear relationship. That positive linear relationship is not on the residual graph, but on the but appears on the scatter plot. The residual graph, please don't forget, is going to be centered at 0. And if we were to center this one at 0, it would look something like this. We'd have a couple here, then we'd have a little further, and we get all the way out here, and we're getting pretty far away. All right, so this would be the residual plot, where it's centered on 0. We have a horizontal line, and while we don't see a shape, we definitely see a pattern because our variation is changing. All right. Number 32, a large store has a customer service department where customers can go to ask for help with store-related issues. According to the store records, approximately 1/4 of all customers go to the service department for help finding an item. Assume the reason each customer goes to the service department is independent from customer to customer. Based on the approximation, what is the probability that at least one of the next 4 customers who go to the service department will ask for help in finding an item? So basically we could have 0 ask for help, 1 ask for help, 2, 3, or 4. But they're saying at least 1. So they want to have the probability of 1, the probability of 2, the probability of 3, and the probability of 4. And technically this is a binomial. All right, technically this is a binomial. Our probability of the probability is 0.25. And basically, we could set this up as a binomial, but unfortunately, they did this type of math work, which makes it a little bit more difficult to recognize. So we're going to do 1 minus the probability that 0 wanted help? Well, first off, this is the probability of wanting help. The probability of not wanting help is 0.75. But we have how many customers? Well, we have 4. So 1 minus 0.75 to the fourth, or 1 minus 3/4 to the fourth. Because basically all 4, none of them could ask for help. Essentially, we're going 1 minus first customer, second customer, third customer, fourth customer. And this is 3/4, 3/4, and 3/4, and 3/4. Because they don't want help, they don't want help, they don't want help. And 1 minus the probability of none of them wanting help is going to be 1 minus 3/4 to the fourth power. If we were doing this as a binomial CDF, we'd go, well, 1 minus the probability of this. Well, this is going to be 4 choose 0, 0.25 to the 0, 0.75 to the fourth. That's working it as a binomial. 1 minus, I need to know that this value 4 choose 0 is 1. So 1 times 1 minus, this is also 1. And this is 0.75 to the fourth. So 1 minus 0.75 to the fourth. Either way, whether I go about it through a logic process or a binomial process, I will get the same answer. The problem is I have to know that 4 choose 0 is 1. 10 choose 0 is also 1. Anything choose 0 is 1. Okay? All right, moving on to number 33. Data were collected from a longitudinal study designed to investigate the relationship between blood sugar levels and brain shrinkage. The results of an analysis of the data for 22 observations are shown in the table below. So which of the following represent a 98% confidence interval for the slope of the least squares regression line for brain shrinkage on blood sugar levels? Assume the conditions for inference are met. So when we're doing this, it's basically beta hat plus or minus T star times the standard error. Well, beta hat is our slope of the regression line, and the constant is always going to be our y-intercept. This is always our y-intercept. So when you see the constant, it's y-intercept. So we're going to be looking only at this row. So we have 0.161 plus or minus, we'll come back to T star in a moment, and our standard error is 0.073. Now, we need to be real careful with this. We're working with a regression, and so our degrees of freedom are n minus 2. So in this case, 22 minus 2, so our degrees of freedom are 20. So now we can go ahead and calculate our T star. And they wanted us to do a 98%. So second vars, inverse T, parenthesis 1 minus 0.98, close parenthesis, divided by 2. Degrees of freedom were 22 minus 2 or just 20, 22 minus 2, or if you wanted to type in 20 directly, that's fine. And we end up getting 2.527. 2.5279. All right. So with that said, the 0.161 gets rid of this. And we have a 0.073. And 33 should be C. All right, 2.5279. Please make sure that for regression and regression only, you're using degrees of freedom of n minus 2. All right, number 34. In a certain computer card game, the player is awarded 5 points for each card that is moved to a correct position. All right. the player is penalized 10 points for each minute the game is played. Let X represent the number of cards moved to the correct. So these is correct. This is minutes. All right. And they're getting a minus 10 points, and they're getting a plus 5 points here. Assume X and Y are independent. What are the expected value and standard deviation of the points per game? So basically, at this point, we're going to go, well, for our equation is essentially 5X minus 10Y. So we're going to do the mean. And we can go 5 times 9.5 minus 10 times 5.4. And if we do that real quickly using the calculator, 5 times 9.5 minus 10 times 5.4, we end up getting a negative 6.5. Well, that gets rid of C, D, and E. They're gone. So then I have, so we know we have our mean, but now we need to do our standard deviation. Well, first off, let's rewrite our equation. And we now have 5 times 12.9 minus 10 times 1.1. First off, we have to be really careful. We can't subtract. We have to add them. So now my new standard deviation is, and I'm going to go ahead and multiply these out. 5 times 12.9 equals 64.5. Because we can multiply by a constant. So this is the standard deviation for X. And this is my standard deviation for Y, which is 10 times 1.1, or just 11. But remember, we can't just add them directly. We have to square them and then take the square root. So 64.5 squared plus 11 squared. Take the square root of that, and I end up getting 65.4. So my answer to number 34 is B. My answer to 34 is B. All right, problem 35. A program that was intended to cure a person's fear of spiders was offered at a local zoo. Volunteers with a fear of spiders participated in the program, which included holding a spider for 15 minutes. 1 month after they completed the program, the participants were contacted and surveyed about the program. Over 90% of the participants claimed they were cured of their fear of spiders. Based on the description of the program, which of the following statements is true? Okay, because over 90% of the participants claim to be cured, the results prove that holding a spider will cure a person's fear of spiders. Well, please remember, to be an experiment, we have to have a comparison group. We don't have any sort of comparison group. So this is not an experiment. All right, there is no other treatment group. Because over 90% of the participants claim to be cured, the results can be generalized to the population. Once again, not an experiment, because as such, it cannot be generalized to the population. Because the participants were volunteers, the study is a census. No, it's not a census of all the people, because we'd have to take everybody for it to be a census. Because the participants were self-selected, in other words, they chose to participate, a person's desire to be cured could be a confounding variable. That is a true statement. All right. Number 36. A police officer uses a motion detector, a radar gun, and I guess we don't like the word gun, to indicate whether a car is traveling faster than the speed limit. A speeding ticket will be issued to the driver of the car if the officer believes the driver is speeding, as indicated by the detector. The situation is similar to using a null and alternative hypothesis to decide whether to issue a speeding ticket. The hypothesis can be stated as follows. The null, we believe they're innocent, they're not speeding. The alternative, they are speeding. What best describes power of the test? Well, first off, what is power of the test? Power of the test is correctly rejecting a false null. So in this case, rejecting the null means we believe the driver is speeding and we did it correctly, which means they are speeding. So the probability of issuing a ticket to a driver who is speeding. So correctly rejecting this, believing this. If we believe this, what's the officer going to do? They're going to write them a ticket. All right. So power of the test is correctly rejecting a false null. 36 is A. 37. An agricultural scientist wanted to compare the effect of a new fertilizer to that of three older fertilizers, X, Y, and Z, on the growth of vegetables typically grown in small gardens. 200 green bean seedlings were individually planted in identical plots and randomly assigned to one of the four groups of 50 each. Seedlings in one group were given the new fertilizer, and the three remaining groups of seedlings were given X, Y, or Z, respectively. At the end of 4 weeks, all seedlings were dried and weighed. The scientists found that the mean weight of the seedlings in the group given the new fertilizer was significantly greater than the mean weights of the seedlings in the other three groups. The scientists concluded that the new fertilizer was more effective than the other fertilizers for all vegetables. Why is the scientist's conclusion not appropriate? The study was an observational. No, the study was definitely an experiment. They randomly assigned treatments. The study was observational. No, it was definitely an experiment. The experiment only included green beans, so the results cannot be generalized to all vegetables. This is true. It can be generalized to green beans of that type. So it can be only generalized to green beans, not to all vegetables. 38. In a physics experiment, two different methods were used to measure the angle of deflection when a subatomic particle collides with a certain material. I sound smarter just saying that. We know I'm not. 10 specimens of the material were used to compare the two methods. For each specimen, the angle of deflection was measured using both methods. For each specimen, the method used first was determined by the flip of a fair coin. The difference between the measured angles were calculated for each specimen. A test of the hypothesis that the population mean difference is zero had a p-value of 0.082. The hypothesis test described here had three components: the number of specimens, the sample standard deviation of the differences, and the magnitude of the sample mean differences. Compared to the tests described, which of the following would have resulted in a smaller p-value? So let's go ahead and talk about some of these terms. Because first off, they've done everything they possibly can to confuse you with their terminology. So we basically have x bar 1 minus x bar 2 over S1 squared N1 plus S2 squared N2. Now, what things actually change our p-value? As these get farther and farther apart, as this gets farther and farther apart, our p-value goes up. This is known as the magnitude, that distance. So as magnitude increases, p-value goes down. We're more and more, as this gets farther and farther apart, we're more likely to reject, which means we have a smaller p-value. So as magnitude goes up, p-value goes down. As standard error, as standard deviation goes up, as S goes up, p-value goes up. So if we want if S goes down, p-value goes down. And then as N goes up, our p-value goes down. So we're looking for a smaller p-value. So to get a smaller p-value, we need our magnitude to go up. We want this to happen. We want our standard deviation to go down, and we'd like our sample size to go up. That's what we need to happen. So let's read these. The number of specimens and the sample standard deviation of the differences remain the same, okay? But the magnitude was smaller. No, we need magnitude to go up. The number of specimens and the magnitude of the differences remained the same, but the standard deviation was larger. No, we need standard deviation to go down. C, the number of specimens remained the same, but the magnitude was smaller. No, we don't want the magnitude smaller. We want the magnitude to go up. The number of specimens remained the same, but the magnitude of the sample mean difference was larger. That's good. And the sample standard deviation was smaller. And we definitely want the sample standard deviation to be smaller, which is D. So 38 does work. All right, so 38 does satisfy. Okay, on to number 39. A polling agency reported that 66% of adults living in the United States were satisfied with their health care plans. The estimate was taken from a random sample of 1,542 adults in the United States, and the 95% confidence interval for the population proportion was this. So between 63 and 68% of adults were happy according to this poll. Which of the following statements is a correct interpretation of the confidence level? So I see the word confidence level and I start thinking in repeated sampling or taking all samples. And remember, we don't like saying probability. The probability, and so I'd rather say, you know what, probably not this one. As soon as I see probability, I kind of stop reading unless I have to come back. Approximately 95% of random samples of the same size from the population will result in a confidence interval that includes the proportion of all adults living in the United States who are satisfied with their healthcare plans. This sounds pretty good. This sounds like this is a good possibility right there. Let's keep going. Approximately 95% of random samples of the same size from the population will result in a confidence interval that includes the proportion of all adults in the sample. No, we don't want the sample. We want the sample of all adults. I mean, we want the population, so all adults. So that says sample, that's a bad answer. Approximately 95% of all random samples of adults living in the United States will indicate between. No, every sample is different. They're not going to have the same endpoints. All right. Approximately 95% of all random samples of adults living in the United States will result in a sample proportion. No, they're all going to have different. Every sample is different. We're not going to have the same sample proportions. The only answer choice that works is B. All right, number 40. A survey was conducted in a large city to investigate the population and to investigate public opinion on banning the use of trans fat in restaurant cooking. A random sample of 230 city residents with school-age children. So I'm going to write C for children. We have a sample of 230 was selected, and another random sample without children. So without. And that sample was size 341. Of those with school-age children, 94 opposed. So 94 were opposed to banning trans fat. Whereas, and 147 of those without children were opposed. An appropriate hypothesis test was conducted to investigate whether there was a difference between the two groups of residents in their opposition to the banning of trans fat. Is there convincing statistical evidence a difference between the two population proportions? So this tells me I have a 2 proportion z-test. And that's what I'm going to need to run at a significance level of 0.05. So let's go ahead and go to our calculator. Stat test 2 proportion z-test. 94 out of 230, 147 out of 341. And they're looking for a difference. So basically our null hypothesis is P children equals P without children. HA, P children is different than P without children. So I need to make sure I have not equal highlighted. I calculate and I get a p-value of 0.595. 0.595 alpha, and they said an alpha level of 0.05. This is greater, so we're going to fail to reject the null. Which means there's not sufficient evidence. So, is there convincing statistical evidence? And the answer is no. No, because because the probability of observing a difference at least as large as the sample, a difference if the two populations are the same, is greater than 0.05. Yes. Matter of fact, our probability, there's a 59.5% chance of observing a statistical difference at least as large if the two populations proportions are the same. So 40 is D. All right, that ends this video and this test. Thank you.